Okay, guys, so listen, this is video number 2 on our series of 3 videos on reviewing ionic compounds. Yesterday, in the video I posted on Tuesday, we drew some Lewis dot structures. We got a beginning understanding of how we could write the formulas and write the names for ionic compounds, which are always metals on the left-hand side, with the non-metals on the right-hand side. So let's just quickly review here. If I wanted to combine beryllium with our friend nitrogen, I'd look and see where they are on the periodic table. Beryllium is in the second column, has 2 valence electrons, which would mean it would be a +2 charge. And nitrogen is in the column 15 with 5 valence electrons, which everybody wants to get to 8. So this guy would gain 3 electrons because that would give it 8. And so now I need to think about how can I combine +2s for the beryllium with -3s for the nitrogen. And the reason that I wrote out 3 of these and 2 of these is because we're always seeking balance, right? This adds up to give me 0 net charge, and that's what we want in an ionic compound, right? We're finding a home for all of the electrons that are given from the metals to the non-metals. So the nitrogen is going to take electrons from the beryllium. So at this point, I recognize that the formula for this would have to be that there are 3 berylliums, because I need to have 3 +2s to cancel out the 2 -3s. And the name for this, the naming scheme for all ionic compounds, is you put the element name for the first part, the metal is always just the element name, beryllium, and then you change the name of the second element. You change the name of the nonmetal, and you end it in IDE. Now, some of them are a little tricky. You wouldn't write nitrogenide because that just sounds weird. We just go with nitride, okay? Now, that is relatively straightforward. But the beauty of this periodic table, if you don't know where I got this particular periodic table from, it is on your Canvas homepage. It's the very as you look in the calendar, it's probably in the middle of November, and it says, periodic table, print this out. The reason this one's so cool is because the second page, which is upside down, has all of this amazing information about both ionic, acidic, and molecular compounds. Now, we're currently talking about molecular compounds, and we'll review these prefixes real soon. But this is the mother lode that I want to focus on a good bit of time today. Polyatomic ions, guys. These are ions, okay? But they are made up of multiple elements. This one, the carbonate ion, is a carbon attached to 3 oxygens, and they combine together have a -2 charge. So what does all of this mean? Well, I can go back to my normal old periodic table, and let's just kind of pick our friend potassium, all right? And so I'm going to go ahead and say potassium is K with a +1 charge. And let's say that potassium, which would be the cation, remember cats are positive, cations are positive, cats walk on paws. Let's say I wanted to combine that potassium ion with a carbonate ion, which is going to be CO3 with a -2 charge. So I'm going to go ahead and think about how I would write that formula. +1 and -2, that doesn't balance out. So, but if I do just a tiny bit of thinking, if I have 2 of the potassiums, each potassium is +1, that's going to cancel out the CO3. And so that's the formula. And what would I call this thing? I just call it potassium carbonate. And that's it. All right, let's do a couple more with some polyatomic ions. We'll start out with going from formula to name. Let's go ahead and take our friend calcium, which is right here in column 2, which means that the calcium is going to have a +2 charge. And let's do one that's a little bit trickier, right? I'm going to go ahead and combine calcium with our friend and notice this is an important point. There is a very close similarity between phosphite and phosphate. Phosphite is PO3 with a -3 charge. Phosphate is PO4 with a -3 charge. So you have to be super careful about looking at these names and doing it correctly. So let's go ahead and let's do calcium with phosphite, the PO3 with a -3 charge. So how would that look as we think about this? PO3 with a -3 charge, phosphite. Well, pretty clearly +2 and -3 aren't going to balance out, but if I get 3 of the +2s and 2 of the -3s, now here's a key point. I have to put parentheses around the PO3 because I need 2 of them. They're a gang, they're a posse, they like to stick together. So the formula for this would be Ca3PO32. And again, calcium phosphite. Right. Okay, so look, that's ionic compounds with a little bit of a polyatomic ion thrown in for some good measure. Now let's go in the opposite direction. I'm going to give you a name and let's see if we can come up with the formula. So let's say that I wanted to discuss with you and figure out strontium and let me sneak a peek here. Which one do I want to choose? Let's do strontium. We could do strontium sulfate. I like it. Okay. So first off, if that's the name, now I need to figure out the formula. So I look up strontium on the periodic table. Strontium is right here, Sr. It's in column number 2, so that means that the Sr is going to have a +2 charge. I go to the back of my periodic table, I go to page 2, and I look up sulfate. I find sulfate right here, SO4 with a -2 charge. And I made this one too easy for you. You're welcome. So I would go ahead and write SO4. I'm going to put the -2 charge underneath. I'm going to see that that is nice and balanced. So the formula is just SrSO4, strontium sulfate. Done and done. Right? Now, what if we have one that isn't quite so nice? How about we do a little bit of... I just want to find one that I don't necessarily always use. Oh, yes. Okay, let's do that one. Let's go ahead and do aluminum oxalate. This is where you start to really sound like a chemist. Aluminum. Yes, go into the lab and get yourself some aluminum oxalate. All right. So step 1, we find aluminum right here in column 13, which means it has 3 valence electrons, which means it's going to be a +3 charge. It's going to give up those 3 valence electrons. So I'm going to write Al. I'm going to put a little +3 underneath it. Oxalate, that's not an element. That's one of these polyatomic ions. And I zoom right in here on oxalate, which is C2O4 with a -2 charge. C2O4 with a -2 charge. Now, unfortunately, the +3 and the -2, those aren't going to cancel each other out. But with a little bit of thought, I can totally figure out that by doing 2 of the aluminums and 3 of the oxalates, 2 of these, and again, because I need multiples of these, I have to put this in parentheses. I need 3 of the oxalates. That's going to give me an even charge, a charge of 0. 6 and 6 cancels out. And so that would be the formula for aluminum oxalate. All right, so look, that's a quick going over of polyatomic ions. But kind of like the commercials, but wait, there's more. Because one of the big things that we've not hit on yet is the land of the transition metals. And this is really where students get mixed up, all right? Now, one thing that I wish these had that don't, right? Copper, right? Silver, and gold. All right, we're going to go ahead and put +1s on them. All right, those guys form +1 ions, all right? And zinc, cadmium, and mercury, we can form +2 ions. All right? Those we can go ahead and just kind of put And you know what? Mercury is actually a little bit sneaky. I'll leave that one off. But if I'm elsewhere in here, we've got some issues. And the reason is because these d orbital electrons, they don't behave quite like the others. They don't follow the same rules, and it's a little bit tricky. So if we wanted to go ahead and talk about an ionic compound that involves a transition metal, we don't know the charge of the transition metals based on where they are. They don't follow the rules that the other ones did, whereas if I'm in the first column, I'm going to be +1. If I'm in the second column, I'm in +2. Just because I'm in column number 6, that really doesn't mean much of anything, all right? So let me go ahead and give you a couple of examples of how we can write ionic compounds for our friends, the transition metals. So let's go ahead and play with a little bit of chromium here. So let's say that I had the following formula: Cr3O2, right? Well, at first you're like, well, I don't know what the charge on the chromium is because it's one of these transition metals. I can't tell what the charge is. So when you look at a compound that has a transition metal in it, you're going to have to do a little bit of homework. The nice thing is we do know the charge on oxygen. That charge is -2. And because there are 2 of them, and this is actually a terrible formula, Mr. Caldwell is not thinking very clearly. Let me go ahead and just get rid of the 3 there. Sorry about that, guys. So if I have O2, that means that oxygen has a charge of -2. I'm going to write it twice because there are 2 of them. And now I need to be thinking, well, chromium has to balance out a total of -4, which means the only possible answer for the charge on the chromium is +4. So what we had to do here was just some deductive work, some sleuthing, some detective work. And so in order to determine the name of this, we're going to definitely call it chromium. We're going to definitely call it chromium oxide. But this is the sneaky part. We're going to use Roman numerals. And I'm going to insert that Roman numeral right here. And the Roman numeral for 4 is IV. So if you don't know Roman numerals, I is 1, II is 2, III is 3, IV is 4, V is 5. And typically we don't need to go much beyond that, but just realize VI is 6, VII is 7, and I'm not going to go above 8, so let's just go ahead and take it to 8, VII. So we have to use Roman numerals to determine, or excuse me, to show what the charge is on an ionic compound that is involving a transition metal. So now let's go ahead and play with our friend. How about yttrium? That's a cool one. That's the letter Y. So let's say that we have the following formula. Y. I want to make sure I'm not being silly here. Y5. Oh, I don't know that I want to do all that. Sorry. How about we go with Y2 S3. All right, so let's see what that gets us. I don't know the charge on the yttrium, but I do know the charge on S. S is sitting over here in the same column as oxygen, so it's going to be a -2 charge. I've got 3 of them, so I'm looking to cancel out a total of -6. The only way I can get rid of -6, and I have to do it in 2 sort of swoops. If each of the yttriums was +3, a +3 and a +3 would cancel out a -2, -2, -2. So what I've just figured out by using my noggin is that yttrium, and I can never remember how to spell that, Y-T-T-R-I-U-M. This would be yttrium, and let's be careful. The Roman numeral is the charge. it's not the number of yttriums, right? Remember we wrote chromium 4 because chromium was +4. It's not that there were 4 chromiums. Chromium has a +4 charge. So this would be yttrium, Roman numeral 3, sulfide. All right, now let's play it the other way. What if I give you a compound name? Let's see if we can write the formula. All right, so let's go ahead and see. And this one always throws students off, right? They want to think that magnesium, Mg, and manganese are the same thing. They are not. So let's say that I have manganese, can't spell, manganese 4 IV chloride. Well, we know that the chloride means I'm coming from chlorine, which is right here, which is going to be a charge of -1. And so I know that the Cl has a charge of -1. I know that the Mn, manganese, has a charge of +4. Clearly not balanced. So what I'm going to do is I'm going to think about getting some more chlorines. How many more chlorines? Well, a total of 4. So the formula for manganese 4 chloride would be MnCl4. All right. And let's try one last one here. Let's go with some iron. And how about we go with some iron 2 phosphide? Iron 2 phosphide. And so if you want to pause the video and think about that for a moment, go ahead and I'll walk you through it. Iron is going to be Fe with a +2 charge. Phosphide is going to be P with a -3 charge because of where it's located in the periodic table. And so I'm thinking that I'm probably going to want to have 3 of those suckers to cancel out 2 of those suckers. All right. So take a deep breath. All right. This is a lot of stuff, but we are making good progress. And now I'm going to put this stuff together, the stuff that I did at the beginning with the polyatomics, the stuff that I've done here recently with these Roman numerals and the transition metals, and let's just see if we can make it all happen together. So the last little bit, let's go ahead and really swing for the fences here. Right? Let's go ahead and see what happens when we put our friend titanium. Right? And let's say that we put that titanium with our friend perchlorate, which is sitting right up here at ClO4 -1. And if I go ahead and write that this is Ti4 ClO4, all right? And I want to double check to make sure I wrote that right. Yep. So at first you're like, I don't know what this is. Well, yes, you do, all right? You know that the Ti is titanium. So I've given you a formula, and now I want to know the name. Titanium, right? And then I look on the back and I'm like, oh, ClO4. ClO4, that has a -1 charge, and it's called perchlorate. So I'm going to write titanium perchlorate. And I wish I'd left myself a little bit of space because I forgot there's a Roman numeral I'm supposed to put in there. So let's go through this, and you know what? Mr. Caldwell is a nincompoop. He meant to put the 4 on the ClO4, guys. Sorry about that. So let's think. I've got a -1 charge because perchlorate, ClO4, is a -1 charge. The formula says that there are 4 of them. 1, 2, 3, 4. So I've got to cancel out a total of -4. So guess what the charge on the titanium is? Because there's only 1 of them. This must be titanium IV. So I should have inserted that in between the tit. So this would be called titanium 4 perchlorate. All right. Whew, that's quite a mouthful. Now let's go in the opposite direction. What if we were talking about I like my friend molybdenum, mostly because it's just a super cool name. Now let me give you a name, molybdenum. And let's say that this is molybdenum 3. and we're going to call it molybdenum 3. And I want to use one of my polyatomics. So we'll go ahead and use dichromate. Dichromate is right here. It's Cr2O7 with a -2 charge. Molybdenum 3 dichromate. So I'm giving you a name, and now I want the formula. So molybdenum is MO. We know it's got a +3 charge because the Roman numerals told me. And what did we say? We said perchlorate? Dichromate. Gosh, I'm getting old. Cr2O7 -2. Cr2O7 with a -2 charge. They're not balanced. And I just have to think, how can I get them to balance? Well, 6 cancels out 6. So how many molybdenums do I need? I need 2 of them. And how many of the dichromates do I need? I need 3 of them. Remember, when you need more than one of a polyatomic ion, you've got to put it in parentheses. Guys, that's 20 minutes. That's a long time to be focused on this stuff. My hope is that this has helped you. And listen, I'll do one more of these where we tie all this together, but we do it with our friends, the make-believe elements, because you're going to have to do it with the make-believe elements on the quiz retake on Friday. Okay, guys, have a good one. Bye-bye.